So we are near to getting at the proper form of the helium ground state. We know the spatial part, two particles in the same 1s independent particle state must be symmetric, because that's the only way you can write it down in this form. That's the only way. And this is symmetric. Therefore, in order to obey the antisymmetric requirement, we have to go into the spin part. That is to say, how we can add two spin half from the electrons. We learned that this is just a reminder. We did that 2 weeks ago, general angular momentum discussion. So for two electrons, we have two spin halves. Thereby, we have four situations. And in our language, using the alpha state, spin state representing up, which is 1, 0. And the first entry is for the electron marked at number 1. So this is alpha 1, alpha 2, both up, and so on. So we have two very funny things called alpha 1, beta 2, and beta 1, alpha 2. Point number 1. Look at this. If I interchange 1 and 2, the two electrons, that becomes alpha 2, beta 1. Before switching, alpha 1, beta 2, after switching, alpha 2, beta 1 has nothing to do with each other. It's not symmetric. It is not antisymmetric. Okay, that's why on this line, I marked if we interchange the two electrons, this is automatically symmetric spin part. This is automatically symmetric, but this two has no symmetry property. I just mark a horizontal line there. That means neither symmetric nor antisymmetric. But we can form linear combinations of them. We learned that. There is a symmetric linear combination, there's an antisymmetric linear combination, and in turn, these three, I mean this one, these three symmetric ones form the spin triplet. Total angular momentum quantum number being s equals 1. Half plus half give you 1, the longer one. Okay, and the Z component has 3 components, and it is these 3 symmetric ones. This is called the spin triplet. There's another one with S equals 0 and MS equals 0, a single spin state that is called spin singlet. That is antisymmetric. Now, we have a way to write down the proper, the legal helium ground state within independent particle approximation. The spatial part discussed, both are in 1s. This is symmetric. It must go with an antisymmetric spin part, and there's only one choice. So this is a unique ground state. No other choice. It also means it is non-degenerate. That's the only case you can write it out. And let me tell you, this is what chemistry books, when you see this picture, really means. Of course, when you first see this, they would not tell you what it means. You need, a few years of quantum mechanics maturity in order to really understand what this simple picture, putting 2 electrons in the 1s and 1 up, 1 down, as Pauli said. Okay, so this is the proper way of understanding such a simple cartoon picture of the helium ground state. And now, let's have a very important treats on this unique ground state. All right. Now, think about it this way. I'm going to multiply that out. So I have 1SR1, 1SR2, and then alpha 1, beta 2, one term. And then I have this thing, beta 1, alpha 2, the second term, and with a minus sign. All right. So this is what I did here. So the first line is nothing but my previous unique ground state. And now, when I see 1s up, 1s with spin up, I label them with all the quantum number, just as what you learned in the previous course in hydrogen. So I can put them as 1s. I should put, this is not a 1, sorry, this is an up, okay? So please correct it. It's up, okay? And it also proved that I'm trying to improve the notes every year. This is a new page. All right, so now, if you want the full label, this is n equals 1, L equals 0, ML equals 0. There's a S equals half omitted, and then up means MS is plus half. So when I see 1s beta, I call it 1s down, and similarly 1s down here, and then 1s up here. Okay, so this can be written as this form. Nothing, I'm just rewriting the equation. But all of a sudden, we realize that this can be written as a determinant. I can arrange, I have two possible single particle states when I include spin in the label. One is 1s up, one is 1s down. So I have 1s up horizontally in a row, and then I have 1s down horizontally in a row. What I mean is that these two are both 1s down. But I have two electrons, thereby there are two sets of coordinates we call 1 and 2. So I can just fill in 1, 2, and 1, 2 here. And then you can expand this. This terms times this is the first term. Then this term times this term is the second term. And that is the way how you expand a 2 by 2 determinant. Okay, so let me summarize. This is an important treat. I just convinced you that this is the only way to write down the ground state of two electrons, two electron wave functions. And then we realize this can be rewritten as a determinant. Let me introduce the name first. This is called the Slater determinant after John Slater, who was the MIT head of department for 20 years. 1930 to 1950 or so, and built up MIT's reputation as we know it now. And he wrote a lot of quantum theory of atoms, quantum theory of molecules, quantum theory of matter, solid. It means several sets of textbooks. They are very good, okay? Now, so let's go back to here. We can write it as a determinant. Now, if you know a little bit of determinant mathematics, you know this is automatically antisymmetric for the reason. If we switch the two electrons, it means write 1 into 2 and 2 into 1. Immediately you see it is equivalent to interchanging two columns, right? And once upon a time, when you learn determinant, this is, well, the first property or so. You switch two columns, the determinant is off by a sign. You know that, right? So this is a very clever way to construct 3 electron wave function, 4 electron wave function, or n electron wave functions. Okay? So certainly we have some way to do it. And therefore, it is interesting to see whether the determinant also implies Pauli exclusion principle. And here it is. I hope this is another point of breakthrough in your knowledge. You have learned or heard of Pauli exclusion principle many times in different subjects. And here we will see that the antisymmetric requirement of the electron wave function is a higher level statement that implies the Pauli exclusion principle. So let's see how it goes. So in the heading, I emphasize that the Pauli exclusion principle is a byproduct. I'm trying to downgrade it a little bit so as to emphasize the principle lies in the antisymmetric requirement of the electron wave function. So it's a byproduct. In the special case of using independent particle approximation, so that we have single electron states to talk about. So let's go back to the determinant one and ask, what if we put 2 electrons both in up or down? Okay, and actually there's a third one, you know that is the up down plus down up one. And then is this one okay? You know that it's not okay, right? And how can we see it out from our writing of the 2 electron wave function? So if this were allowed, we would have written the wave function as follows. Both electron will be in 1s up. So I can write that, okay, this is up, but I only have one state now. So the second row is also up, okay? Now I put the 2 electrons both in these 2 states. My later determinant will be something like this. You write it out, this minus that, this is identically 0. What I mean by identically 0 is that it is 0, no matter what this coordinates, the actual places of these 2 electrons are, become irrelevant. It is 0 always. But when the wave function is 0 always, your 2 particles disappeared. You don't have any particles to play with. You have 2 electrons. All right? So something is wrong. It is unphysical. And it is because of this, it implies the Pauli exclusion principle. This is not allowed. Or simply put, in the selected determinant, you cannot have 2 states, single particle state being the same. You can easily generalize it to 3 particle, 4 electron selected determinants. We will do that. I will show you later. Okay? So we have learned new things today. Electron wave function antisymmetric, that is a general principle. In terms of single electron states, those we obtained from independent particle approximation. We have the label 1s, 2s, and so on. Okay, we know how to write it out. It's a Slater determinant. Third thing, Pauli exclusion principle is just a byproduct in the selected determinant form of many electron wave functions. Get this message, then go home and think about the whole thing again to convince yourself that it's very logical. Okay? So now, let's generalize this selected determinant a little bit. In the ground state, we have both spatial part being 1s. But as you already anticipate, it works for any two different states, right? So I have 1s up, which is different from 1s down. So I have two different states. Let's label it A and B. Okay, and therefore, this will be automatically antisymmetric. The square root 2 here is for normalization if each one of these single particle states is itself properly normalized. So this is the selected determinant involving any two different single particle states A and B. So that is a generalization. And then the antisymmetric property is very obvious. Determinant property, interchanging two columns, is a minus sign, done, okay? Power exclusion principle automatically covered, because if these two states were the same, A equals B, then you have identical columns or rows, and that will be identically zero. All the particles disappear, sorry, okay? That is not legal, all right? So that is a power exclusion principle. Now, as a byproduct, let's think about, we talk about antisymmetric total wave function. Another important point, I think, is how about forming symmetric wave functions? All right, now, a very simple way is the following. From the Slater determinant, after you expand it, turn all the sign to positive. Now, you have a minus sign here, right? But if you want a symmetric one, turn it to positive, then you will get the symmetric one, right? So now I did that, and this is a symmetric one. All right, if A and B are of different states, you switch 1 and 2, first term becomes second, second term becomes first. This is symmetric. If A and B are the same state, this is automatically symmetric. You don't need to do anything more, right? Okay, so this is the way to construct symmetric n-particle wave functions. This is important for bosons. Now, I would like to back up on our discussion of the helium ground state. Why we were so lucky. We don't need to consider the spin part in our variational calculation or perturbation field. We are not ignorant, but I just don't want to bring out the spin part too early to confuse with the concept of how to handle interactions. Now we know the proper form. In addition to the space part we used, there is a spin singlet part. And the helium Hamiltonian is this. These are the single particle part. I just don't want it to be too long. There are two terms here, two terms here. This is the fifth term. Notice one thing. The helium Hamiltonian is spin independent. There is no electron spin in all these terms. So when we do the expectation value, formally, we need to use the full wave function on the left-hand side, star on the right-hand side, integrate over everything. When we see a spin part, we can multiply the spin part, the inner product, so-called. Okay? However, because this is spin independent, so when we do the expectation value, this will take in an inner product with itself. And this is already normalized. That inner product is just a 1. Thereby, we are left with a spatial integral to do, and that's come back to what we did in the previous sections. So we were not only lucky because I know the physics, and then I don't want to bring out the spin part too early, okay? So we are doing fine. And then if we carry on the ground state energy calculation, we need to use the full Hamiltonian of helium and then our spatial part ground state on either side. Okay, so in this context, you immediately see the ground state energy is related to 3 integrals, one with H1. Well, this R2 will integrate to 1. It has nothing to do with R2, so you are left with this. The second term, you are left with this. But R2, R1 are dummy variables to integrate over. In these 2 integrals, they are actually the same. I represent it by I1, R2, and actually it's 2 times I. The third one is the integral that we interpret classically within electromagnetism. That is the Coulomb, direct Coulomb integral. So we also know that the ground state energy should be given by this. Okay, now keep this in mind. We will do some excited state physics, and you will see, in addition to this term, the exchange integral or indirect Coulomb will appear, and that is very quantum, no classical interpretation. Okay, so there's some big physics to follow. Advertisement, you see some entangled spin state. So this is an entangled state. Each electron spin does not have its own reality. We don't know. Well, it doesn't know whether it is up or down. And then we will see it is the origin of ferromagnetism. And then later on in excited state discussion, we know the exchange term will appear. So when we do the self-consistent calculation as we discussed, the exchange term will appear. That approximation is called Hartree-Fock, and that is what the Fock term means. So let's generalize. How about multi-electron wave functions? 3 electrons in ABC, 3 different states. How to write it? It's easy, just like this. If you know how to expand determinant, there are 6 terms here. Okay, and each term has a different sign. I think there are 3 plus 3 minus sign terms. Okay, and then those minus sign, make sure that when you interchange any 2, 1 with 2, 1 with 3, 2 with 3, any possible one, is off by a sign. It's easy to see because of determinant mathematics. How about n electrons in n states? Okay, go to the exercise class this week. The TA will show how to write this kind of thing, and then convince you that this is anti-symmetric, and then how to write the symmetric form. For those who want to learn higher level quantum mechanics, something like second quantization, things like that, that is the beginning. You have to write down an n electron wave function in a proper way. And that is the proper way. Okay? A final remark before we move on. We have seen the helium ground state situation. It is a very simple situation with 2 electrons, and we have seen it is possible to factorize the 2 electron wave function into spatial part times spin part. Key point, don't think that 3 electron wave function can do that, 4 electron wave functions can do that. Sorry, generally it's not true. What am I saying? Now you can think of about a lithium ground state, for example. A is 1s up, B is 1s down, C, let's say, is 2s up. So you have this three states. You have 6 terms, write it out, see whether you can factorize it into space part only or spin part only. Try. Okay, what I'm telling here is, in general, multi-electron wave function cannot be factorized into spin part times spatial part. 2 electrons, okay, it can be done. And that's why we make use of this helium case very often to bring out the physics more clearly. Last, some connection to your thermal and statistical physics course again. We know that there's some relationship between antisymmetric wave function and the fermions. Because antisymmetric wave function implies Pauli exclusion principle, and Pauli exclusion principle means for fermions, if we have a number of them, they must fill the available energy states and stack up in energy. Once an up-down goes into here, the third one cannot go into there. All right. So if you have a large number of fermions, even if they are non-interacting, there's no Coulomb thing. They are just happen to be spin half. Pauli exclusion principle comes in because antisymmetric wave function, they must stack up in energy. All right, this is ground state. Ground state means 0 temperature physics, lowest possible energy state. Okay, but for bosons, there's no symmetric wave function. There's no Pauli exclusion principle. Thereby, the ground state would be put all the bosons onto the lowest possible state. Immediately, you see whether the wave function is antisymmetric or symmetric is very important in statistical physics, even 0 temperature physics. No energy, very well, that is 0. Right? And then this is very high energy, but the temperature is 0. Same. Okay. In statistical physics, you have the Fermi-Dirac distribution to represent this way of filling things. I think you have seen the Fermi-Dirac distribution. Something like that with energy. Okay. So this is 1, this is 0. Okay. What does it mean? The physical meaning of Fermi-Dirac distribution is this, is that a single particle, the probability that the single particle state is filled by one fermion. All right, now look at this. If I use this axis as energy, because this is energy axis here, and this is whether it is filled or not, the probability that it is filled. So here, it is 1 because they are filled. Okay, and then up to this, it is 0 because these are empty. Do you see that this is the Fermi-Dirac distribution? Okay, so that is something that you will learn in Professor Gore's course in a while. The very last page is for those who read some astrophysics. Look at the fermion or electron case. So when a star dies, no more fusion process, energy sources, then there is some gravitational pull. The system becomes present, okay? And then there's electrons in there. It happens that these electrons, fermions, Pauli exclusion principle, could provide a pressure opposing the gravitational pull. In all the books that you read in astrophysics or a popular science book, that is called the degenerate pressure. So what is it? You can understand it even without statistical physics, because the zero temperature physics of electrons already carry high energy. So this is zero temperature physics. We have a lot of electrons. They must stack up in energy. All right. So we can add up the energy, and there's a total energy. So consider a cube. This is our cubical star. We have n electrons in it. They are non-interacting because that's the only problem we know how to solve particle in a three-dimensional box. So you fill in all these electrons, you get a total energy that I call energy as a function of the volume of the box. Now you squeeze the box. L becomes L minus delta L, smaller. Thereby the volume also becomes smaller. Notice that the L lives in the denominator down there. You squeeze the box a little bit, this single particle state is squeezed farther apart and up in energy. That's why I depict it as, more separated than here. You have the same number of electrons. Again, it fills the same number of levels. Because the energy levels are squeezed farther high in energy, the total energy is higher. All right, so no squeezing, one energy, you squeeze it, higher energy. Squeeze the system, energy goes up, thermodynamics, parcel U, parcel V, PDV work done. So it is minus du dV, that is a pressure. You see, you do have a pressure even with zero temperature electrons. Not for bosons. Bosons they don't work this way. But fortunately, we have electrons, and therefore you have this story about the dying star. We have some degenerate pressure due to electrons opposing gravitational collapse. Okay? And even further dying, and after the supernova, you have the neutron star. The neutrons are fermions, and that will keep the neutron star that big. That is another situation of fermions. So we started to see some big physics coming out from this anti-symmetric requirement of electron wave function. The next big physics consequence of this same requirement is most clearly brought up by considering excited state. It's low energy excited states, not the high one of helium atom. Again, let's think what's going on. We may be thinking about putting one electron into the independent particle picture to 2s. So we have a situation of one electron in 1s, another electron in 2s. That will be an excited state of helium. The question is, how can we write down the correct wave functions of this two electron system? Okay? The first page is just to recap what we did in the last 20 minutes. This is the ground state. It is unique. It is a spin singlet. S equals 0. Just to remind you, the term symbol of the ground state is, it is a 1s state. You add up the orbital angular momentum is 0, so it's a big capital S in the middle. It is a spin singlet, S equals 0, 2s plus 1 is 1, so it's the upper thing. It's L equals 0, S equals 0, the total J is only 0. This is this lower thing. So when you see a data table, term symbol of helium ground state is this one. But more generally, after we see that the ground state is a spatial part times a spin part, in general, we have these possibilities summarized in this box. We have seen this case in the ground state. Symmetric spin, spatial part, anti-symmetric spin part. But there's another possibility. How about anti-symmetric space part and symmetric spin part? That will be a spin triplet state. If we have this case, the total wave function is still okay. It is anti-symmetric. And in considering the excited state, we have to consider both possibilities. Both are possible. So let's see why both are possible. We are thinking about one electron in spatial 1s and in another in 2s. Therefore, in the spatial wave function, we have two different states. This is our phi A, phi B thing, okay? So this is phi 1s, phi 2s. The spin part, we will separate, factorize it out and consider it later. So these are spin wave functions, two different ones. So we have a spatial symmetric wave function by having a plus sign in the middle. So this is 1s, 2s plus flipping the R1, R2 the second term. This is automatically symmetric, okay? But I want to emphasize here, this is the spatial part, okay? Fine. This is spatial part symmetric, just like our ground state. It goes with the spin singlet. That will be total anti-symmetric. One state. But there's another possibility. Given me 1s, 2s, I can form an anti-symmetric spatial state like this. Tried it, R1, R2 interchange is off by a minus sign, so it is anti-symmetric. Then it goes with the spin triplet. The total will be okay, anti-symmetric. Therefore, we have a triplet excited state. There are three states, okay? So for this simple excited state, one electron in 1s, one electron in 2s, actually we can write down four legal two electron wave functions. One is a singlet, spatial part is symmetric. One is a singlet, a triplet, three states. The spatial part is anti-symmetric. In general chemistry books, you will see pictures like this. And this is what these four states really mean in quantum mechanics. So it follows there are some non-trivial questions. We have two possibilities. We have the helium Hamiltonian. The question is, will this expectation value of the energy, the Hamiltonian and this one, will they have the same value or different energies? So this is the first question, number one. Let me tell you the answer. They have slightly different energy. and that is the origin of ferromagnetism. And then, how to determine self-consistently this 1s, 2s single particle states. That will be the fork approximation kicks in. In what follows, I will do a not so technical discussion because many of these are concepts to prepare you for further learning if you choose to do so in quantum mechanics or in other atomic molecular physics. So the first thing I would like to bring out is the following. I want to complete this part because the sample questions that the TA will do is closely related to what we will do here. We have two situations: symmetric space part, anti-symmetric space part. I would like to do a common sense discussion on symmetric space part wave function, what is the key feature, as well as anti-symmetric space part. So here, I write down what we have for the symmetric space part. We have two different states, 1s, 2s, with a plus sign. Okay? Again, that will require 7 dimensions to draw it out. We cannot do that. Again, we play the trick. Let's 2 particles live only on 1 dimension, on the x-axis. I have 2 particles, 1 and 2. They are confined in a harmonic oscillator potential. So 1 will be in the ground state, 1 will be in the first excited state. Easy enough, right? So it is the analogy, 1s, 2s. So 1 particle is in harmonic ground state. I draw it out for you. I write it out for you here. This is harmonic oscillator ground state. This is harmonic oscillator excited state, first excited state. So now, how can we form a symmetric 2-particle spatial wave function? We know how to do it. We must do this plus this. If you only have 1 term, you flip x1, x2. It has no symmetry property at all. It's not symmetric, it's not anti-symmetric, it's nothing. Okay, so this is the proper way. Writing it out, I have x1 in ground state, x2 in the first excited state, therefore I have an extra x here. Similarly, for the second term, I have x1 in the first excited state, I have the x1 here. Okay, now, to help you see the picture that follows, particle number 1 live in x-axis, number 2 live in x-axis, they live on the same axis. So I can plot things out like this. x1, x2, the third axis is this thing square. Understand? Okay, symmetric. Notice that there is a diagonal line referring to the 2 particles at the same place, x1 equals x2. So let's look at this symmetric form. In the next problem set, you will be asked to plot some 3-dimensional plots. If you don't have a tool in your hands, go to the exercise class. I hope the TA will tell you some existing and free of charge tools to do so. So here, I simply plot out this thing square. So this is the x1 axis, this is the x2 axis, this thing is the third axis. In particular, take a top view. Using a color so-called contour plot, the top view will look like this. This is the wave function. This is wave function square. The point is the following. if you follow the diagonal axis, I'm trying to write something. Okay, follow this line. This line is the x1 equals x2 line. Do you see big peaks lie on this line? And also, near this line on both sides, the wave functions squared are quite big. All right, now that is the common sense I emphasize about symmetric spatial part. The two particles like each other. They want, well, the probability of finding the two particles to be close to each other is high. They do not interact. There's no attraction between them. The only fact that the spatial wave function is symmetric has the effect that the two particles will be found closer to each other. Take this point with you. In contrary, how about antisymmetric spatial part? Again, one particle in ground state oscillator, one particle in excited state oscillator state with a minus sign in between. Otherwise, the whole expression is the same. I think I have left out some normalization 1 over square root 2, things like that, okay? But doesn't matter, scale the picture. The left-hand side is this square, probability density. Again, this is very important point, punchline of the whole discussion. Look at the x1 equals x2 line, diagonal, okay? Do you see that along this valley, it is a valley, phi x1, x2 is actually 0 there. That is to say, you cannot, 0 probability of finding the two particles to be at the same place when the wave function is antisymmetric, the spatial part is antisymmetric. That is to say, when the spatial part is antisymmetric, the two particles tend to avoid each other. Okay, now this is quantum mechanics, high-level quantum mechanics common sense. You ought to be 20 years old, 21 years old to understand it. You need to build up your knowledge. That's what I mean. Okay, but here at this point, you can use your quantum mechanics knowledge to write down something of the right symmetry. You can use some tool to plot it out. You can actually get a good sense out of it. Okay, so in statistical physics and thermal physics, later on in Professor Gore's course, you will learn something called ideal Fermi gas. Ideal means the fermions are not interacting. But still, Fermi gas is very different from classical ideal gas for the reason, Pauli exclusion principle. They don't like each other. They pile up in energy. All this description are actually the same in physics behind the scene. Okay? In ideal Bode's gas, the particles don't interact with each other, but the wave function must be symmetric. They tend to like each other, so much so that there's something called condensation occurs. Okay? So you see the two subjects are closely related. In quantum mechanics, we do zero temperature physics most of the time, ground state. Okay? So I would like to use 2 minutes to answer the first question that I posed. Is the singlet state or the triplet state have the same energy or different energy? Okay, now the answer is quite clear. They have different energy. Why? Because the spatial part, they are different in symmetry. And why does it matter? Okay, now that's the punchline. We just saw that when the spatial part is symmetric, the two electrons tend to live closer to each other, right? But in the calculation of the energy expectation value, there is a Coulomb repulsive term, E squared over R1 minus R2. For the spatial symmetric part, R1 minus R2 is on average shorter. The Coulomb term will be bigger, positive. This term is positive. Bigger means higher in energy. For the spatial antisymmetric part, they tend to avoid each other. Thereby, R1 minus R2 is slightly longer. The Coulomb repulsive term is less big, less positive. Conclusion. This will have lower energy than that because the electrons tend to naturally avoid each other. This goes with the triplet spin state. Therefore, the triplet state has a lower energy than the singlet state when we take into account the fifth term in the helium Hamiltonian, E squared over R1 minus R2. You see, big physics and non-trivial. But if you follow the argument, it is a big step forward in your maturity in learning physics. We need not do very complicated calculation. I will write down the expression for you next time. But by physical argument, we already get a good answer. And it is experimental fact as well. So conclusion, singlet has a lower energy than the triplet has a lower energy than the singlet excited state involving 1s, 2s. Last statement. This is the spin quantum number s equal 1 state. It has a lower energy than s equals 0. This state has the two spin half tend to align, lower energy. S equals 0 has the two spin tend to anti-align, higher energy. That is the origin of ferromagnetism. Why the electron spin tend to be aligned in a magnetic material. That has to do with this discussion. Okay, so I will stop here today. And then if you have questions, you are welcome to ask.